Alright, lesson 5.09, proving parallelogram properties. So let's go ahead and take a look at parallelogram properties as a whole. And these are things that we've referenced in the past when we talked about specific parallelograms like a rhombus or a rectangle or a square. But we know that there are 5 principal properties. Having said that, one of the most important ones, and the one that ultimately defines a parallelogram, is that opposite sides are parallel. The other 4 are properties that a parallelogram actually has. So we know that the opposite sides are going to be parallel, the opposite sides are congruent, the opposite angles are congruent, and the consecutive angles are supplementary. We also know the diagonals bisect each other, right? So we have in the example down here, opposite sides are congruent. That's represented by this one right here. Opposite sides, of course, are parallel. And in this particular case, you can represent that with the same diagram or the one you have over here as well, where we have opposite sides being parallel like this or like this. That's also true. Consecutive interior angles, using the diagram over there on the right, for example, angle A and angle D are supplementary, angle A and angle B are supplementary, angle B and angle C are supplementary, and angle C and angle D are supplementary. And as you can also see, the opposite angles are congruent as well. Of course, the diagonals also will bisect each other as well. As you can see right there, they've indicated that. That's always true for any parallelogram. It just so happens that with a rectangle and a square, the diagonals are also congruent. So with that being the case, that's the reference page that I would refer to when thinking about the properties of a parallelogram and answering questions about parallelograms, such as the following. Which of the following must be true for a parallelogram ABCD? So we have angle BAC. Angle BAC is this angle right here, is congruent to DAC. So angle DAC is over here. That is actually not true for a parallelogram, because we don't necessarily know if it's a rhombus or square or a rectangle, right? So the diagonal is not going to bisect that particular angle per se, so we have no idea whether that's true or not. So this actually cannot be asserted as being true just because it's a parallelogram. AC is congruent to BD. So another feature that we're being targeted with here is the diagonal AC congruent to the diagonal BD. That is also something that we cannot assert. And again, you can refer back to your property slides if you wish to confer that. It never says the diagonals are congruent. Nor does it say that the diagonals bisect the angles. So that's why those don't work. The last one is AE is congruent to EC. So AE is congruent to EC. This actually is true because we know the diagonals bisect each other. So this half does equal that half, and this half equals that half. So this is going to be the option we want to select. Okay, so kind of looking at another example of a parallelogram. FGHI is a parallelogram with FH being the diagonal, which is the entire length of F to H, which is 8, and the angle FEG. FEG is this angle right here at 83 degrees. So we notice, of course, that FE is half of FH, so that would be 4. So that's the length of FE. So we're simply saying that if the full length across is 8, right, which we're told that it is, then each half, of course, is 4, which it should be because that's by implication, right? You say half, it means half of that. Now when you're talking about the angle, we are looking for the angle FEI. FEI would be this angle right here. So notice that those two angles form a linear pair, meaning they form a straight line, in other words. So their sum has to be equal to 180. So by subtracting 83 from 180, you get the remaining angle value, which is 97 degrees, which is what this degree value is. And as you can see, this degree would also be 97, and this degree down here would also be 83 because they're vertical with each other. So you can find out what all 4 angles there in the middle actually have to be as a result of that fact. Looking at another example, we're going to go ahead and determine in the parallelogram ABCD, angle A is 37 degrees and angle B is 143 degrees. I would highly recommend that you pay attention to this particular slide in reference to your exit ticket. So We know that opposite angles are congruent, so the measure of angle C is going to equal the measure of angle A. Therefore, the measure of angle C is equal to 37 degrees. Remember, opposite angles are congruent. This is true for any parallelogram. We also see the measure of angle D would be congruent to the measure of angle B for the exact same reason. So that means the measure of angle D is 143 degrees. Now if you pay attention, that makes really quite a bit of sense, because remember, this is a parallelogram, so these are parallel sides, these are parallel sides. Therefore, these are same side interior, which means they have to be supplementary, they have to have a sum of 180, as well as these have to have a sum of 180, which is why they both work. Also, these have to have a sum of 180, and these have to have a sum of 180, and that checks out there. So that is the reason why A is 37, or in this case C is 37, and the reason why D is 143 degrees. Opposite angles are congruent is an easy way to justify for both of these, right? So it's good for this one as a reason, it's good for that one as a reason, because it is a parallelogram. Again, pay attention to this particular slide for your exit ticket. In this example, we're focusing on the diagonals, so DE is 7 and AC is 12. So we're trying to find DB. So DB is the entire length across. So we know that DB would be equal to 2 times DE. So therefore you get 2 times 7, or 14. Why is that? Well, because diagonals bisect each other, right? The reason why this works the way that it does is diagonals bisect each other. So because they bisect each other, we know that that's a half of that diagonal. So the other half has to also be 7, which is why the full length is 14. On the flip side, of course, for the exact same reason, let's draw a more distinct color here, blue. We are told that AC is 12 for the entire length, right? So all of that is 12. So AC is equal to 2 times EC. Well, that's also the same thing as saying 1/2 of AC is equal to EC. So since AC is 12, we know that EC is going to end up being equal to 6. For the exact same reason, in fact. We know that the diagonals bisect each other, so of course that indicates that if you're given half of it, then you can, or the whole amount I should say, if you give the entire diagonal length, then you can obviously take half of that and find the half length that we're looking for there, which we are. So looking at what we've learned so far, just keep in mind that with parallelograms, these angles do come into play. And in this particular video, I'm not going to go through any proofs of any kind, but I'm just going to remind you that when you're dealing with parallelograms, you are also bringing into play these types of angle relationships that can in fact occur. Now, having said that, going back to a parallelogram in a general sense, here's another parallelogram, and notice that we are looking at angle B as 78 degrees. I'm actually only required to have this one angle to find all of the other angles, and it's because of these parallel lines and the relationships that I just referenced moments ago. For example, I know that this angle right here is the supplement to 78. That means that the angle at angle A has to be the same exact measure. That would be the difference between 180 and 78, which is 102. Why is that? Well, because that particular angle has to be supplementary to it. They both have to have a sum of 180, so the other angle has to be 102. Likewise, since I now know both of those angles, I know that the opposite angle to 78 over here, D, is also 78, and I know the opposite angle to A, which is angle C, is 102 degrees. That's the reason why it's easy to determine what those degree values actually are, and that's because we're using opposite angles as well, which is what I'm emphasizing here. So you can see how it's kind of like a domino effect, how you can actually find all of the angle values from just knowing one single angle value inside of a parallelogram. Now let's take a look at an application in the coordinate plane. Here we have a parallelogram ABCD, and we want to know the coordinates of point E. Now that point E is the midpoint of both of the diagonals AC and BD. However, we only need to find the midpoint of one of the two diagonals. So for example, pay attention to the order that they listed this in, A, B, C, D. Every other letter represents, in this particular case, a segment that represents the diagonal. So either AC or BD are what we're interested in. So you can kind of have your choice of the letter here, because if you want to find the midpoint, we could just choose the coordinates for example, A and C if we wanted to. And we're using the midpoint formula right there. So to find the midpoint, we take the x value, which is -4, and we're going to add that to the x value of 0 and divide by 2. Take the y value of +4, the y value of 0, and divide by 2. So it might be prudent, if you have to remind yourself, to write this as x1, y1, and this as x2, y2. That is certainly helpful for you here. And then we can simplify that midpoint, right? So we get -4 over 2, +4 over 2, and that just gets us -2, 2 for our midpoint location. So we know that this is going to be the correct answer for the location of E. So E is actually going to end up being -2, +2. This is something I would refer to as one of your help slides for your exit ticket question set that you have. I would highly recommend you refer to this when you're reviewing for your exit ticket question. Okay, let's take a look at another example here. In this last example, we have measure of angle A and measure of angle B provided as 2x and 5x plus 5. So this just kind of applies back to what we talked about earlier when we know that they add up to create 180 degrees, right? Because together they're going to create a straight line, or in this case, we know that they are same side interior angles, right? So same side interior angles is another justification for why we're able to do the following, right? We know that the measure of angle A plus the measure of angle B is equal to 180 degrees. So therefore we can plug in the value of A, we can plug in the value of B, and their sum is 180. So here we get 7x plus 5 equal to 180, and we can go ahead and subtract 5 on both sides. So here we get 7x is equal to 175, and then we can go ahead and divide by 2, or in this case by 7, I should say. So once we divide by 7, I end up with x is equal to 25. So if I'm looking for the value of x, or I'm solving for the value of x, I now know, of course, that x has to equal 25 as a value, and that's because those angles are same side interior to each other, because these are parallel lines, and those are angles that lie on the same side of this particular transversal right here that you can see, A to B. Okay, in this last example, we're told that DAB is this angle right here. So DAB is the entire angle, 5x plus 12, and BCD is 7x minus 28. We have to, of course, set these equal to each other because these are opposite angles, right? So opposite angles are going to be congruent to each other. In this case, we're going to say measures because they're equal. So we take 5x plus the 12, we set that equal to the 7x minus 28, like so. And we can go ahead and get our x term on the same side. So for me, I'm going to subtract 5x on both sides like that. Nice and neat. And we have 12 right here equal to 2x minus 28. Going to go ahead and add 28 to both sides like so. And you don't have to do this little diagram. I'm just showing you because some students like to see that. We have 40 equals to 2x. And then we can go ahead and divide both sides by 2. So now we get x is equal to 20. So we have a value of x equal to 20 in this particular case. And if you had to verify that, you get 112 in this case for both angle values, so that's why it works the way that it does. And that's going to be it as far as that particular example is concerned. So that's kind of showing you opposite angles are congruent within parallelograms versus same side interior angles, right? See, these are just opposite angles in a parallelogram. Okay, so here's your exit ticket. Your exit ticket says for the first problem, in parallelogram ABCD, you have two angles expressed, and you have to find the measure of angle C. I highly recommend that you draw the figure because it can help when you're setting it up, right? So like an example could be an arbitrary parallelogram structure like this, for example. It doesn't have to be like a specific shape, but this is a great example of that. And then you can start labeling, right? So you have 37 degrees for angle A, rather, and you have measure of angle B is 143. I highly refer you to go back to the previous slide that we discussed because we talked about this very problem as an application. As far as the coordinates that you see over there on the far right for your parallelogram, keep in mind that I did recommend that you remember your midpoint formula, so x1 plus x2 divided by 2, y1 plus y2 divided by 2. And again, I highly recommend that you think about what we did in that example when we were talking about parallelogram ABCD, how I paired up certain ordered pairs as my diagonals, right? So you're thinking about the diagonals here. You want to figure that one out, figure out what are the diagonals, and you only have to do that once. For the first two questions that give me the degree values that I see there, especially for the third question, again, I would refer back to the actual slides where I discuss those exact types of problems. I give good examples for those in the video itself, so I'd refer back to that particular part of the video itself when you're trying to get help on that. And so that's going to be lesson 5.09, exit ticket for proving parallelogram properties.